In this video, I would like to talk about two things: entropy and integration. Now, this is an important video because it contains everything we have learned so far and combines it into one thing. By the way, all the videos here are important. It is just that this video is extremely important. Any Bayesian localization algorithm is comprised from two different processes or functions. The first function or process is called sense. In that function, we receive data from the sensors, so we add information to the system, so we can better localize ourselves. The second function or process is called move, and in this process, I move my robot and I reduce or decrease the information. And again, if you remember from the previous videos, when I add movement to the system, I always add uncertainty. Why? Because an exact motion is just like a unicorn. It doesn't exist in real life. So we had a function called sense, which receives data from the sensors. And we had a function move that moves the robot, but adds uncertainty. What happens is that every time that I run the sense function or receive data from the sensors, I add information. I know more regarding the robot states, and again, I decrease the uncertainty. The sense function is supposed to update the probability or distribution of being at any point according to the sensors. But wait, update according to what? To the previous states. And this is where the nature of Bayes' law comes into play. This is why I add at the beginning an initial belief. In the examples we have seen so far, the initial belief was a uniform distribution, meaning that I knew nothing regarding the initial state of the system. Initial beliefs are in fact my first guess or first estimation. Anyway, sense always adds information. The more I sense and the better my sensors are, the more accurately I will know where am I. The problem is that our robot has to move. Again, otherwise it's not a self-driving car, it's a self-not-moving car. Each time our robot moves, it loses information. If you remember why from the previous video, it is because every time we move in a stochastic world, we add uncertainty into the system. I thought that I moved only one bin or one unit, but maybe I moved 2 bins or 3 bins. I thought that I moved 5 bins, but maybe I overshooted and moved 6 or 7 bins. So in reality, Bayesian filters are in fact changing between these two functions, from sense to move, from move to sense. Sense will increase our level of certainty, increase the amount of information, and move will decrease it. Sense increases, move decreases. This is precisely the reason that we are in a Bayesian algorithm. After all, Bayes' law talks about the probability of H given E. And this is exactly the case here. Meaning, in each iteration of sense and move, I'm asking myself, where am I currently, or what is the probability that I'm at position X if I know, yes, given if I know that at the previous iteration I was at position Y. This is what Bayesian filters are all about. Now, how does all of this relate to the concept of information entropy? Entropy, if you don't remember, is a scientific concept and a measurable physical property that is most commonly associated with a state of randomness or disorder. But in our world, an information entropy talks about something a little bit different. Given a random variable, entropy asks how random this variable is. If the variable isn't random at all, the entropy will be 0. The entropy will increase as the variable gets more and more random. Let's give a concrete and classical example, which is, of course, flipping a coin. So let's assume that I have a fair coin and I flip it. It can be either heads or tail. If the coin is completely fair, meaning the probability of heads equals to the probability of tails equals 50%, then the entropy marked as h of x will be at its maximum value, which is 1. But what happens if the coin is not a fair coin? By the way, a fair coin is only a mathematical creature that doesn't exist in real life. For example, if you flip an American quarter many times, you will see that approximately in 70% of the times, the coin will come up heads. Now, if I have an American quarter, the level or the value of the entropy decreases. Why? Because it is not a uniform distribution between heads and tail. I know that the chances for heads are much bigger than the chances for tail. Therefore, I reduce the entropy because I reduce the uncertainty. I am more certain that the coin will come up heads than tail. If I have a gimme coin which has heads on both sides, then I know what the outcome will be. When I flip such a coin, I don't actually have any uncertainty. I'm sure that it will be heads. Therefore, when the probability is 1, the entropy will be 0. But in our case, when the probability is also 0, the entropy will be 0. Why? Because it doesn't matter if the probability is 0, because in our case, I know for sure what the outcome will be. Okay? If the probability for tails is 0, I know for a fact that the coin will be heads. Therefore, the entropy will be 0. In the world of Bayesian algorithms, the sense process always decreases the entropy, and the move process always increases the entropy. Now, how do I calculate the information entropy? According to this formula, h of x equals minus, and this minus is important, minus sigma p of x log p of x. And the log is a log base 2. So let's give an example. Let's say I'm in a 5-bin world and I have no clue where am I. No clue means a uniform distribution, which is basically point 2 over here, point 2 here, point 2 here, etc. In our example, if I inject the numbers into the formula, I get h of x equals approximately 2.3. Now, what happens if I know that I'm at bin number 3? The equation becomes this. Okay? And the answer is 0. Pay attention that for all the bins beside bin number 3, the probability is 0. Therefore, the sum will be 0 in any place besides bin number 3. If I know where the robot is, the level of randomness is 0. If I know that I'm at bin number 3, there is no entropy, or the entropy will be 0. Why? Because I know for sure where am I. So, in the following exercise, I will ask you to write a function that computes the entropy of an arbitrary histogram distribution. Good luck!